Hi all, my name is Goodwin, and I just wanted to thank you for coming to my presentation. In recent years, machine learning algorithms have become increasingly frequent in the field of healthcare. The most common healthcare use cases for machine learning are automating medical billing, clinical decision support, and the development of clinical care guidelines. In this presentation, we will be focusing our attention on the field of radiology, really focusing in on medical imaging in the machine learning realm. So what are we doing here exactly? When radiologists go to work every day, they read X-ray images and make diagnoses for their patients. In a nutshell, what we're hoping to do is build a computer model that can perform this same task. We'll be asking questions like, can our model view an image like a radiologist, and from that picture diagnose a healthy set of lungs or a set of lungs with pneumonia? To start this project, we needed to find some data. We'll be using the chest X-ray pneumonia dataset, which was compiled by Kaggle user Paul Mooney. The dataset is organized into 3 folders, train, test, and val, and contains subfolders for each image category, pneumonia or normal. In total, there are 5,863 X-ray images in JPEGs and 2 categories of photos, pneumonia and normal. Chest X-ray images were selected from respective cohorts of pediatric patients of 1 to 5 years old from Guangzhou Women and Children's Medical Center in Guangzhou. All chest X-ray imaging was performed as part of a patient's routine clinical care. For the analysis of chest X-ray images, all chest radiographs were initially screened for quality control by removing all low-quality or unreadable scans. The diagnoses for the images were then graded by 2 expert physicians before being cleared for training the AI system. In order to account for any grading errors, the evaluation set was also checked by a 3rd expert. Now that we have the data, we have to actually use it. In order to do this, we created a loop in Python that would iterate over the different file paths and load the images into our datasets. We had to make it so that these images were machine readable, so we used RGB formatting. We chose an image size of 150 pixels by 150 pixels. In an RGB format, this means that each image was compiled of an array of size 150, 153. The first 2 values match the pixels of the image. The 3rd value is set to 3, as each pixel is represented as a combination of 3 colors, red, blue, and green. In addition to this, we also had to enumerate our labels. We did this simply by labeling the normal images as 0 and the pneumonia images as 1. Our next step was to use the shuffle function within sklearn. Shuffling data serves the purpose of reducing variance and making sure that models remain general and overfit less. Because of how the images were stored, our datasets were sorted by class, i.e., all of the normal images were uploaded first. We needed to shuffle to make sure that our training and test data sets were representative of the overall distribution of the data. The final step was to divide the values in our image arrays by 255. This would allow us to be able to plot the images in Python. When all was said and done, we had 5,216 images in our training data set and 624 in our test data set. Once we had all of our data loaded, I wanted to take a look at 2 quick plots just to make sure everything loaded properly. The first is a simple bar graph showing how our data is distributed. As you can see here, we have a nice breakdown of normal and pneumonia images. The blue bars correspond to the training data set, while the orange bars correspond to the test data set. In both instances, we can see that there are approximately double the amount of pneumonia images than there are normal. I'm not sure what to make of that at this point, but definitely something to consider as we move forward with this project. But it is good to know that we have a good number of both normal and pneumonia lungs. The second plot is personally just something that I found interesting And that was simply just plotting a subset of our images within Python. A few steps ago, when we divided the values in our array by 255, that made it so we were actually able to plot what looked like pictures. As you can see here, we were able to plot a visual representation of each image. Now, there's no real insight to gain from this, but I just found it interesting to display the power of the tools that we have at our disposal. Loading the data the way that we did allows for us to actually graph these images like we would graph a bar graph or a scatter plot, and the end result is the actual image in front of our eyes. Now that we have all of our data ready to go, the next step was to create the model. We have decided to use a Keras sequential model. A sequential model is appropriate for a plain stack of layers where each layer has exactly one input tensor and one output tensor, which is ideal for our setup. On the right here, you can see a screenshot of our code outlining all the layers that we added to our model. We then compiled our model using the Atom optimizer and the sparse categorical cross-entropy loss function. The Atom method is computationally efficient, has little memory requirement, is invariant to diagonal rescaling of gradients, and is well suited for problems that are large in terms of data or parameters. The loss function we chose computes the cross-entropy loss between the labels and predictions. This cross-entropy loss function should be used when there are two or more labels provided as integers. Once again, this fits our problem perfectly. We then had to fit our model to our training data sets. Based on the model setup, we used a batch size of 64. I also chose to run 15 epochs. This was just a personal decision based on the computational power I had available to me and what I thought was a good number to start with. We also had a validation split of 0.2, meaning that 80% of our data was used to train and 20% was used for validation purposes. After finalizing our model and running through the 15 epochs, it was time to evaluate how our model performed. We used the history instance to create a pandas data frame of our evaluation metrics, and then plotted these values. The result was the following graph that you see on your screen now. As we can see, our graphs indicate that our model was working well. The accuracy increased for each of the epochs, and the loss decreased. You can also see that these values somewhat flattened out. To me, that means including more epochs probably would have resulted in some overfitting, so I think we're okay with the 15 that we chose. Since our model looks pretty good, the next step is predicting values based on the test data. I use the predict classes instance, which will predict which label should be assigned to the test images. This led to the following confusion matrix that you see on your screen now. So what can we gather from this confusion matrix? First off, let's just look at the overall accuracy. This was calculated to be roughly 0.74, meaning that our model correctly predicted 74% of the labels for the images. To me, I think that is a good starting point for sure. I am happy with these results for our first attempt. Is that as accurate as a radiologist predicting these images? I would assume no. But we are certainly taking steps in the right direction with our model. Now let's break it down by label. When predicting a healthy set of lungs, our model had a precision of 0.99. Our model predicted the lungs to be healthy 73 times, and 72 of those were correct. That is definitely great. However, when we look at the pneumonia predictions, we see that we only had a precision of 0.71 or 71%. Our model predicted the lungs to be pneumatic 551 times, and 389 of those were correct predictions. Since the ultimate goal of our model was to accurately diagnose pneumonia cases, we perhaps failed in this regard. So where do we go from here? What are our next steps? Our initial model had a 74% accuracy, as I said, which I believe to be good but not great. Our model was incredibly accurate when predicting a healthy set of lungs, but struggled a bit when trying to diagnose pneumonia. What could be some of the reasons why? My first thought is that perhaps we did not have enough training images. If we had, say, 10,000 images to look at, I feel like that could probably improve our accuracy. Now, it may be difficult to find a data set with more than the 5,000 plus images that we are given here, so this might not be a realistic fix. Another option is perhaps we need more epochs to fit our model. I chose 15, and like I said, I believe any more could have resulted in some overfitting of the model, but perhaps I'm wrong and the model actually needs more epochs and needs more time to converge and develop. This would be a simple enough fix and something that we could definitely test in the future. Perhaps the model that we chose isn't the best. In my research this week, I believe I chose the proper layers, optimizer, and loss function. However, maybe I am incorrect. I am still somewhat of a novice with this technology, so perhaps we could speak to someone who has a better knowledge of Keras in order to help optimize our model. The options are definitely there, but I think we have set an excellent groundwork for some important work here. Deep neural networks are now the state-of-the-art machine learning models across a variety of areas, from image analysis to natural language processing, and widely deployed in academia and industry. These developments have a huge potential for medical imaging technology, medical data analysis, medical diagnostics, and healthcare in general, which are slowly being realized. This ever-expanding field is now being used in radiology, and we have begun developing a machine that can predict as accurate as a radiologist. I'm excited to see the future of this